So in the previous video, we derived the Cauchy-Riemann equations, okay, and we can state a theorem from our derivation. Okay, so this is a theorem from section 2.4, and it goes like this. If f is differentiable at z sub 0, then the Cauchy-Riemann equations are satisfied at z sub 0. Okay, and we can also state that if f is analytic on U, an open set U, then the Cauchy-Riemann equations are valid on that open set U. Okay, so one of the important things about this theorem is that it shows that the Cauchy-Riemann equations are a necessary condition for f to be differentiable. Okay, or for f to, it's a necessary condition for f to be analytic in the open set. Okay, so that would be the contrapositive. So basically, stating the contrapositive of this theorem is that if the Cauchy-Riemann equations do not hold at z sub 0, then f is not differentiable. Okay, so we're going to use that in these couple of examples that we're going to do. The converse of this statement is something that we'll look at later. Okay, so but for now we're going to use the contrapositive to show that a function is not differentiable. Right, so we're going to look at basically the two functions that we looked at in class, which we showed were nowhere differentiable. Okay, so so one of those examples was f of z equal to z bar. Okay, so this function equals z bar, of course. If z is of the form x plus iy, z bar is x minus iy. And so from this, clear to see that u of xy is equal to, so the real part of this function is simply x, and the imaginary part, the function b of xy is equal to minus y. Okay, so I've separated my function into a real part and an imaginary part. All right, well, what is du dx? Du dx is, of course, 1. Okay, and what is dv dy? dv dy is minus 1. And notice that these two things will never equal, okay, for any z, okay, which violates one of the two Cauchy-Riemann equations. Therefore, by this theorem, f of z is nowhere differentiable. We also looked at the function real part of z. Okay, maybe we can actually look at something like the imaginary part of z. And so the imaginary part of z as a function is equal to, this is simply y, right? So in this case, u of xy is equal to y, and v of xy is equal to 0, right? So now I can get a violation of the Cauchy-Riemann equations if I look at du dy, right? So du dy is 1, and dv d anything is 0, of course. So du dy is 1, dv dx is 0, and we have a violation of the Cauchy-Riemann equation. So we can conclude from this that this function, the imaginary part of z, is nowhere differentiable. Okay, much easier than actually using the limit. All right, let's look at a different example that I have here. So, we will show that the function that's equal to f of xy equal to x squared minus y squared minus 2xyi. We'll show that this is not differentiable anywhere? Well, we're going to show that it's not analytic anywhere. Sorry. We're going to show that it's differentiable only at one point. And if it's differentiable only at one point, then it cannot be analytic in an open set. Okay, because remember, to be analytic means that the function is differentiable in an open set, not just at one point. Okay. All right, so if this is our function, we've already split it up into a real part and an imaginary part. So we know what u and v are. So u of xy equals x squared minus y squared. V of xy is equal to minus 2xy. All right, I'm going to find these partial derivatives, and then we'll see, we'll pull in the Cauchy-Riemann equations. But du dx is equal to 2x, and du dy is equal to minus 2y. And dv dx is equal to minus 2y, and dv dy is equal to minus 2x. All right, so the Cauchy-Riemann equations are du dx must equal dv dy. So Cauchy-Riemann, to be valid, means du dx. So we're going to write du dx must equal dv dy. And so we get 2x must equal minus 2x. And our du dy, our other Cauchy-Riemann equation is du dy must equal minus dv dx. And so that would mean minus 2y must equal, so du dy is minus 2y must equal minus a minus 2y, or 2y. So when are these two equations both true? Only at one point. Okay, and that point, of course, is 0, 0. Okay, so we can say that f is differentiable at z equals 0, okay, but f is certainly nowhere analytic because it's not differentiable in any open set.